We conclude our discussion of symmetry with time translation. First, we'll introduce the time translation operator. We'll talk about the Heisenberg picture of quantum mechanics, and then finally talk about time translation invariance. So consider a solution of the time-dependent Schrodinger equation. H of psi of x and t is equal to IH bar partial with respect to t of psi of x and t. We define an operator u of t which propagates the wave function forward in time. U of t applied to psi of x and 0 is equal to psi of x and t. If the Hamiltonian is time independent, we can expand this defining equation as a Taylor series in time. So u of t applied to psi of x and 0 is equal to psi of x and t, and we expand this around time equals 0. So this is equal to sum of from n equals 0 to infinity, 1 over n factorial, partial to the nth power of, with respect to t, of psi of x and t, evaluated at t equals 0 times t to the nth. And we can pull the Hamiltonian through each consecutive time derivative. As an example, we'll do the second n equals 2 derivative. So if we start with psi squared, with partial square with respect to t of psi of x and t, we can expand that out as partial with respect to t of partial with respect to t of psi of x and t. But that is simply the right side of the Schrodinger equation. And so we can replace that with minus I over h bar, Hamiltonian h applied to psi of x and t. If we now pull the time derivative through the Hamiltonian, again, we get minus I over h bar, h times partial with respect to t of psi of x and t. Again, we can take this from the Schrodinger equation, replace it with minus I over h bar times the Hamiltonian. So ultimately, we get minus I over h bar times the Hamiltonian quantity squared applied to psi of x and t. And you can see that for whatever power of n, we can just repeat this n times and get the same quantity, minus I over h bar times the Hamiltonian, applied to the nth power. We can now substitute this back into the sum, giving us that u of t applied to psi of x and 0, that is the times translation of the wave function at time equals 0, is equal to the sum from n equals 0 to infinity, 1 over n factorial, minus I over h bar, ht, all quantity to the nth power, applied to psi of x and 0, because we assign this at t equals 0. This part in front is nothing more than the sum that is equivalent to an exponential. And so this becomes then, you can see that u of t is simply equal to e to the minus I h t over h bar. And therefore, the Hamiltonian is the generator of time translation. The time evolution operator u can then be used to solve the time-dependent Schrodinger equation. We first expand the wave function at time equals 0 using the stationary states of the Hamiltonian. That is, psi of x and 0 is equal to the stationary state psi sub n of x times each coefficient, all summed over all the possible values of n. If we apply a translation by a time t to this wave function, we get that psi of x and t is equal to u of t applied to psi of x and 0. And this is equal to the sum over n, c to the n, u of t applied to psi sub n of x. But this can be replaced by its exponential form, which makes sum over n, c sub n, e to the I, minus I, h t over h bar applied to psi n of t, of x rather. Now, this Hamiltonian has no time dependence. This has no time dependence. But when you apply the Hamiltonian to psi sub n, you get the wave function back again, because it's an eigenfunction of the Hamiltonian, and the eigenvalue e sub n. So this merely becomes the sum over n of c sub n e to the minus I e sub n t over h bar times psi sub n of x. But this is exactly the time dependence that we generated from the separation of variables when we went from a time-dependent equation to a time-independent equation and solved for stationary states, and then used the time evolution function, which is this exponential, to time evolve a complex function, which is a sum of the stationary states. And so with this way, we can easily solve, using the time evolution operator, we get the same solution as we did by doing the separation of variables and solving the time equation independently. So just as with other symmetries, time translation can be applied to operators as well as wave function. This leads to the so-called Heisenberg picture operators. So QH of t is simply Q sandwiched in between U dagger of t, U of t. In the Schrodinger picture of quantum mechanics, the wave function evolves in time according to the equation, the Schrodinger equation. H psi of x and t is equal to IH bar partial with respect to t of psi of x and t. Operators, which are always built from the operator x, position, and the momentum operator, so x and minus I h bar partial with respect to x, have no time dependence. And the time dependence comes only from the time dependence of the wave function itself. If we want to get the expectation value of an operator, we calculate it by sandwiching it between two wave functions that are time dependent. So the expectation value of q at any time t is simply the inner product of q with psi of t on either side. In the Heisenberg picture, we consider the wave function to be constant in time. That is, psi sub h of x is just equal to psi of x and 0 in the Schrodinger form, while operators evolve in time according to q sub h of t is equal to the sandwich of u dagger q u. The time dependence of the expectation value, therefore, is carried by the operators rather than the wave function. Again, if we want to get the expectation value of the operator, we can do that too. The expectation value of q is equal to the wave function, a Heisenberg wave function, sandwiched around q sub h of t. So it's psi h, qh, psi of h, where the t dependence here is explicit. This is merely equal to psi of 0, at time equals 0, of u dagger q u, because we're now expanding back out to the value of q sub h, psi of 0. But then if we move this operator over to the right, and we take this and move its Hermitian conjugate over to the left side, we get u psi 0, q u psi 0. But these are merely the operators, these are merely the wave functions as a function of time. So we can now replace this back and get the same value of the expectation value that we got in the Schrodinger picture. So these two methods are complementary, they're the same, they give the same results, they just look at it from a slightly different perspective. If the Hamiltonian is time dependent, it's still possible to use the time translation operator to solve the Schrodinger equation. So let's see how that's done. The time-dependent translation, the time translation operator is now a little bit more complicated. Suppose we have a wave function at a time t sub 0, and we time translate it to a time t. So psi of x and t is equal to u of t comma t0, so it starts at t0 and moves to t, and translates to t, of psi of x and t0. So you start at t0, you translate it to time t. In this case, the time translation operator for an infinitesimal time delta becomes simply u of t0 plus delta, comma t0, is approximately equal to, and now we take the first two terms of the exponential form, which is 1 minus I over h bar Hamiltonian at t0, because remember it's time dependent, times delta. If the time evolution is independent of the time interval being considered, then we say that there is time translation invariance. And we can write this mathematically as well. We'll do that in a minute. So, what does this mean? If we prepare a system in a state alpha at time t1 and allow it to evolve a time delta, an infinitesimal time delta, to a state beta, it will evolve identically from alpha to beta in the same time delta if we prepare it at a different initial time t2. How do we write this mathematically? We say that the time evolution operator that goes from t1 to t1 plus delta is equivalent to the time evolution operator that goes from t2 to t2 plus delta. According to this expansion, with delta being infinitesimal, you get 1 minus I over h bar times Hamiltonian at t1 times delta equals 1 minus I over h bar, the Hamiltonian at t2 times delta. And these have to be equivalent. It says that the Hamiltonian at t1 then must be equal to the Hamiltonian at t2. So invariance under the operation of time translation operator u of t0 leads to the requirement that the Hamiltonian at t1 is equal to the Hamiltonian at t2 for any two values of t1 and t2, so that the Hamiltonian must be time independent after all, and therefore its time derivative is equivalent to 0. Now, according to the generalized Ehrenfest theorem, the partial with respect to time of the expectation value of the Hamiltonian is equal to I over h bar times the commutator of the Hamiltonian with the Hamiltonian plus the expectation value of the time derivative of the Hamiltonian. Well, these two are both 0, and so this is equal to 0. Therefore, we recover conservation of energy, which is a consequence of time translation invariance. In quantum mechanics, each of the classical conservation laws is related to continuous symmetry of the Hamiltonian, as we've found out by generating all the symmetry operations that are continuous. Translation symmetry leads to conservation of momentum. Rotational symmetry gives you conservation of angular momentum, and time translation symmetry gives you conservation of energy. There are other symmetries in quantum mechanics, discrete symmetries like parity, that give you additional symmetries. Additional symmetries give you additional conservation laws in quantum mechanics, and this is actually a very fundamental and important part of quantum mechanics.